Welcome to Ask and Learn.
In this problem, we have A at a specified state contained in a piston-cylinder device with a set of stops, and the air is heated until it reaches a final temperature. We wish to calculate the amount of heat that is transferred in this problem. So we assume that air is an ideal gas and that the kinetic and potential energy changes are negligible. Air has the properties as follows. The gas constant is 0.287 kilopascal meter cube per kg Kelvin. The specific heat from our table at temperature of 300 Kelvin is 0.718 kilojoule per kg Kelvin. Now, we can take the air as a closed system since there is no mass transfer, and the energy balance equation can be written as follows. The energy in minus the energy out is equal to the change in energy of the system, delta E. Now, the energy in is due to the heat. So the heat transfer Q in minus the energy out, which is the work done at the boundary work, and this is equal to a change in internal energy, delta U. And delta U can be written as the mass of air times the specific heat times the change in temperature, T2 minus T1. Now, we need to calculate the value so we can use this equation. So the volume will be constant until the pressure is 200 kilopascals. So T2 is equal to T1 times P2 over P1. So we can calculate this final temperature. So this temperature is the initial temperature, 296 Kelvin, times 200 kilopascals over 100 kilopascals, and hence we get the temperature at this point to be 592 Kelvin. Now, the mass of the air can be calculated as follows. So the mass of the air, M, is equal to P1 V1 over R T1. So this is the initial pressure, 100 kilopascals, times the initial volume, 0.25 cubic meters, over the gas constant R, 0.287, and that's kilopascal meter cube per kg Kelvin, multiplied by T1, which is 296 Kelvin. So if we do this calculation, we get the mass of the air to be 0.2943 kgs. Now, the boundary work is done during the process 2-3, and the boundary work can be calculated as follows. So the boundary work out of the system is equal to P2 into V3 minus V2, since the volume is not constant in this process. And this is M times R into a difference in temperature, T3 minus T2. So we know the mass of the air, we just calculated that, so that's 0.2943 kg into the gas constant for air, 0.287, and that's again kilopascal meter cubed per kg Kelvin, times the change in temperature from states 3 to 2, 700 minus 592, and that's in Kelvin. So we get the boundary work out of the system to be 9.12 kilojoules. So now if we can go back to our energy balance equation and substitute these values, and hence we can find the heat transfer. So the heat transfer Q is equal to the boundary work plus MC T3 minus T1. And so this is the boundary work we just calculated, 9.12 kilojoules, plus the mass of air, 0.2943 kg, times the specific heat, 0.718 kilojoules per kg Kelvin, times the change in temperature between state 3 and state 1, which is 700 minus 296 Kelvin. Hence we get the heat transfer into the system to be 94.5 kilojoules.